Hello, and welcome back to my Kubernetes series. In video 13.1, we built and reviewed the Dovecot container and its related config maps. In the last video, 13.2, I focused on the synchronization and the ability to create a master-to-master sync relationship. In this video, we will walk through the deployment, rather stateful set, and bring these two components together so they can be deployed in a Kubernetes environment. So let's jump right into that deployment. For that, we'll switch over to my K8s master and change into our Dovecot folder. Let's bring in the declaration of our stateful set with vim dovecot deploy.yaml and paste the contents. It's quite a long file, as you can see. We're going to go back up to the top and start walking through this stateful set. You can see I split the file into a few sections and highlighted the different containers we will be deploying in this implementation. But we'll go through that. Let's start on the top. We are deploying a stateful set, not a deployment, as in most other of my implementations. Only my database is another stateful set. Everything else is either implemented as a deployment or as a daemon set, which deploys one pod per node. We deploy this application in the namespace mail server and call that app obviously Dovecot. We declare a few selectors such as app. I declare a service name and establish that I want 3 replicas. Next, I declare how to create the storage. As I want an individual storage for each container, I am using the volume claim template. I call this persistent volume claim storage and deploy that claim in the mail server namespace. I want a read-write mode and request 5 GB of space. As storage class, I'm addressing my NFS storage provisioner. As we walk through the file, I see that the selector label is in here in this file twice, so I'm going to remove those 4 lines, 27 through 30, as they are only required once. Alright. Following that selector, I declare the template and its subsequent metadata. The next section contains my init container. I need only one for the synchronization. I call this temporary container lsync config and use a busybox image. I set some environment variables that are in line with the whole deployment. For my script that I will show above me again for good measure, requires these values for creating the Lua configuration script for lsync. I set a variable called inst, which represents the instances, and set that value to 3, the number of pods I'm deploying. I need the namespace, the service and the cluster address to include in the Lua configuration file. With that, we get into the script that makes all the magic happen. At first, as these config maps are read-only here, I am copying these files into another directory that allow me to modify them. Then I make the script that I pass into the container executable. Next, I need to save the hostname into a file. I need that value later, and that was the only way to get it. Next, I separate the hostname into a name and a number. As this command is executed on the command line, these two values are then saved as environment variables and will be used in the script afterwards. That determines how many times one of the loops in the script are being run through. Then I execute the script and build the Lua configuration file. Once this script on the command line is executed, we get to the volume mounts. The first volume mount is an empty dir. We used the same functionality in the postfix deployment when we modified the main.cf config map. The next mount is the config .sh, which comes from the configuration map and contains a file with a bash script. That script sets up the Lua config file that lsync needs to configure the sync from each of the Dovecot pods to each of the other two pods. Lastly, I have a base Lua file, which is extended by the script. The next section was there to generate the Diffie-Hellman certificates. As I created these certificates for postfix, I will reuse them here for my Dovecot implementation. That is why this section is out-commented. If I would remember where I have this deployment from, I could elaborate a bit more, but as I could not for the life of me find the source, you see this piece of code here. If you recognize this deployment, feel free to leave that in the comments below. That concludes the init container. Great. Now we get to the main containers and we start with health-z. You can see it is the standard health-z container that executes ns lookup command on a regular basis and makes sure the container, or rather the service, is up. As the service balances the traffic in the background to a pod, at least one of these three instances needs to be up in order for the health probe not to fail. Should it fail, the whole deployment would crash and would have to be restarted. Right after the health container, we have the lsync container. You see the image address first, followed by the image pull policy. I do set my environment variables. They are required for the startup and the creation of the synchronization of data. I need an environment variable inst, which represents the number of instances, and set that variable to 3, as I have 3 replicas. Next, I hand over a variable called keyPath. As indicated, my variable name, that path, which is called keys, is used to exchange the keys between the different instances of Dovecot. The next 3 variables are required to set the destination for the syncs in other pods. They are being pulled in by the startup script and are added to the Lua file as the address where to sync to. Next, we have the volume mounts. First is the storage for the mail, which is quite self-explanatory, followed by the config folder. That folder contains the Lua file that was built by the init container. Next is the key exchange mount, which is a directory that all the different pods share. That shared storage is required to write the keys into a central place that all pods can access and read. These keys will then be read and integrated into the authorized keys file. Once they are part of that file, no login credentials are required to access the other pods, and the sync can be executed flawlessly. The last mount is the local time zone, which should be quite obvious. Lastly, I define port 22 as the SSH port, which is used for the synchronization over SSH. That already concludes the lsync container. This lsync container is followed by the main Dovecot container. This container does provide the IMAP protocol and the inbox for users. We start off with the name and the image repository. That repo is followed by the image pull policy and some readiness and liveness probes with their configs. Then we get into the volume mounts. I will not walk through all of them. Mounting a config map is something at this point I must assume you know how to do. So let's focus on what they do. The first mount is the email storage. All email data is stored on this external storage, which is created through the volume claim template, which we walked through at the beginning of the deployment file. The next mount is the Diffie-Hellman certificate, which we created during the implementation of postfix, and we will reuse these certificates here in this deployment. Next, we mount the SSL certificates that we cloned from the Nextcloud namespace, and lastly, we have the time zone mount. Next, and I separated these config maps to visually be able to distinguish from other mounts, we see all the maps we discussed in video 13.1. All of these mounts represent the configurations you need or might need to make Dovecot work. I will not repeat myself as we discussed these config maps in detail in that previously mentioned video. I will just slowly scroll through the files until we reach the end of this volume mount section. You can see that some of these maps are outcommented. In one of my previous videos, I mentioned I do not need all of these config maps that Dovecot offers. They are part of the deployment or stateful set. I don't need them for my deployment, so I kept them in the file, but outcommented these configurations. If you want to use them, head over to my GitHub, remove the hashtag in front of the line of the file you want to add to your implementation, and deploy the additional config map to your cluster. Next, I declare the ports I need for this implementation. I am declaring the POP3 unencrypted port, the encrypted, as well as the IMAP unencrypted and encrypted port. Then I have two additional ports I am declaring. One is the lmtp port on port 24. That port is being used between postfix and Dovecot to hand over emails that I receive. The next port is the sasl authentication port that is used to verify if a user exists between postfix and Dovecot. Once that is verified, the email is handed over to Dovecot, where it will be saved in the inbox of the user. Next, we have the declaration of the volumes. Again, I won't get into details as this process should be pretty explanatory at this point. Let's just say for each of these files and mounts we have just declared, we need a volume declaration. So I will just scroll down through the file to the end of the volume declaration, which also represents the end of the stateful set. We see a separation line after which I'm declaring a service. That service is called Dovecot, and I am using only the encrypted and unencrypted port 143 and 993. All other ports I ignore and do not need, as I don't use these services, which are the POP3 and SMTP ports. SMTP is already declared and implemented through postfix. During my tests, I thought I needed port 22 as well, but as I'm not using this port through a service and access it from the outside of the namespace, that port is not necessary. But I do need to declare additional services, such as the lmtp port 24 and the sasl authentication port on port 13050. We are at the end of the file and can finally deploy this application in our cluster. After deploying that app, we need to use the deployment to generate the password for the user, add these users to the database, and then we can log in into our mailbox. So let's now write and quit and start deploying all the configuration maps, secrets, and lastly the stateful set. To make life a bit easier, I'm going to bring up the configuration maps on the right hand side and start deploying these maps into the cluster. We'll start with the kubectl apply-f dovecot conf-f. We have to skip the deployment, obviously. That comes last, so next file would be dovecot dict auth conf ext YAML. The next one would be dovecot dict sql, dovecot sql -f lsync lua base and the lsync lua config YAML. Let's deploy these maps first. Next, I'm going to deploy the shared storage through the PVC we have here. kubectl apply-f pvc.yaml. And we're going to verify that. kubectl get pvc-n mail server. We have a pending storage. Okay, we'll keep that. Usually that works out. Next, you can see on the right hand side we have our conf.d folder, so we need to deploy those maps as well. So I'm going to switch into the conf.d folder, and we're going to ls conf.d and have to apply all those maps with kubectl apply-f 10 -f10 director kubectl apply-f 10 logging -f10 mail. Then we have the 10 master. We have the 10 metrics. Next file is the 10 SSL config. Now that we have all the 10s done, let's continue with the 15. kubectl apply-f 15 LDA and 15 nope -f15 mailboxes. Gonna empty the screen and gonna continue kubectl apply-f 20 IMAP 20 lmtp. Oh, there is a -f missing in front of this map. The next one would be 20 managed sieve -f20 pop3 -f20 submission. Gonna get those maps in. kubectl apply. Now we're going to continue with the 90s. aclconf -f90 plugin -f90 quota -f90 sieve conf, and last but not least 90 sieve ext program, and get those maps in. Great, now we only have two left. kubectl apply-f the two auth, one dict and the other one is auth sql conf ext. As we have all those config maps deployed, let's take a quick look into our namespace. kubectl get config maps mail server. Keep in mind we will nope, not yet. -n, of course. We do also get the configuration maps that we deployed for postfix, but we should see a lot of them from our deployment for Dovecot. So we see the 10, 15, 20, 90, auth dict, auth SQL, basic config, that's for the Lua file. We have Dovecot configurations, and that should be it. And then we have the update conf, which is to create the Lua configuration file. As the deployment of these files looks reasonable, let's go back one level. Nope, we need to stay in Dovecot and take a quick look. We should be fine with all our config maps. Now we should be able to apply our deployment, or stateful set rather. We will change on the right hand side back to our watch command. Watch kubectl get all -n mail server. We see our postfix implementation is still in here and running. And now we are going to change the folder here, bring up the list and say to deploy our Dovecot stateful set kubectl apply -f Dovecot deploy YAML. Very exciting moment. Let's see what happens. Here we are again 2 weeks after my last recording. The deployment obviously did not go well and did not start up properly. I ended up leveling my cluster and to start from scratch as I could not figure out why the stateful set did not want to start up. The pending persistent volume claim should have been a major indicator that something was wrong which needed to be investigated. During the restructure and rebuild of the cluster with all its deployments, I found out that a package that I updated on the virtual machines called AppArmor was responsible to prevent traffic to flow from the workers to the master and the other way around. Once I fixed that problem, everything worked again and we can resume where we left off. At first, let's take a look at the PVC and ensure that the storage is bound. We do that with kubectl get pvc-n mail server. As the storage is bound, we will now try to reapply the stateful set to our cluster and get Dovecot to work. As we start the watch on the right hand side with watch kubectl get all-n mail server, we see the application postfix is running. Now we can deploy Dovecot with kubectl apply-f Dovecot deploy YAML. As we hit enter, we see the stateful set appearing and the init container starting up, preparing our lsync synchronization instance. Let's now watch the remainder of this deployment starting up. As the first instance is up and running, we see the second one starting up. I mentioned earlier I need to generate the password through Dovecot for the user to be able to log into their database. So let's now use the first pod and generate this password. Before we can do that, we need to figure out which encryption algorithm to use. We can find that algorithm with kubectl exec-it dovecot 0-c for container, so we're accessing the Dovecot container, and execute the command in there, -n mail server space dov adm password -l for list. We're listing all the possible encryption algorithms. That command gives you a list of the algorithms with which you can encrypt that password. Once you identified that algorithm, you can go ahead and generate a password with kubectl exec-it dovecot 0-c dovecot-n mail server dov adm password -p, and now you provide the password string, and we're going to use password, very innovative, -r, and now we provide the algorithms we want to use, or the algorithm we want to use to encrypt the password. We're going SHA 512. hit enter, and we get the encrypted password for our user. We now have to take this password and put it into our database, create a user in that database, and then we will be able to log in into the mailbox of this user. Whatever encryption algorithm you decide to use, make sure that it aligns with the one you defined in the Dovecot SQL conf ext file. I will show the details above me on the screen. We can now take this password, add it to our database with a user, which will then allow us to log into the mailbox of this particular user. Now that the password is generated, we can copy this part of the credentials and log in into our database. We go to our database folder. And we'll access the database. Use postfix, show tables. We have our virtual users table in which we have to enter those details. The user which we want to create. Need to know what we have to enter. Alright, so we will enter insert into virtual users, local mail. We need the username. We need the password. And we need active values are manual at localhost. The next one is the username, which is manual, followed by, I'm going to capitalize that, by the AES encrypt function. We now enter the password. Of course, that was not possible. So we're going to remove everything, as it was not the last piece I copied. We're going to scroll up on the screen, copy the password, paste it, add the password with which we want to encrypt this password. And add a 1. Select everything from virtual users. We can now see that the entry is right here, and we're good to go. Fantastic. Now that we have entered the user, we can exit our database. And before we start logging into our mailbox, let's quickly verify that the synchronization is actually ready and working. The synchronization with lsync. We can simply test that with log kubectl, of course, kubectl logs dovecot -0-c for container. lsync is the container name, and in the namespace mail server. We can see a lot of output. And we can also see that the incremental file list was sent to the different pods, such as Dovecot 1 and Dovecot 2. Just in case you wonder about the error message, that error message was thrown at a time where the pod Dovecot 2 did not yet exist. Once the pod was successfully started up, you can see the success message on the bottom of the screen. Let us empty our screen. Before we start logging into Dovecot and our mailbox, however, I need to highlight two changes I had to make to the config map Dovecot SQL conf XYAML. If we enter that config map and go down to the SQL command that pulls the username and password, the changes I had to make for one was the password to decrypt the database stored user password has to be in quotes, which I did not have that way. And two, if you select the password with an AES function, the field will return the whole string as field name. In our case, the field name would be AES decrypt in brackets password, comma, and the password to decrypt the first password in quotes. Dovecot does not accept that and wants a field called password as a result. That is why I had to assign the alias password to that field. Only that way Dovecot would let me log in into the mailbox. As that is out of the way, let's now move on to test the login to Dovecot as a user. To log in into a mailbox, we will create a temporary Alpine Linux pod in our namespace mail server. We create this pod with kubectl run it for interactive --tty -rm debug, which is the name, --image equals alpine, which is a base alpine image in the namespace mail server. That way we will be able to see that pod spinning up on the right hand side. We do not want this pod to ever restart, so restart is never, and I need two dashes in front of that. And last but not least, I want to enter the SSH or SH. Let's run this command. You can see the container debug is creating with a name that we specified. We are now on the console as the pod is running, and we are where we want to be. We have to add a package to this pod. The package we need is apk add open SSL. Now the package is being installed. As you can see, that goes really quickly. And once this package is installed, we can now execute and connect to Dovecot. The command we execute to connect to Dovecot is open SSL sclient connect dovecot.mailserver.svc.cluster.local 993. As you can see, we are not addressing any specific pod, but we are addressing the service, which then takes care of routing our traffic to an available pod. Once we hit enter, you get a lot of output, which is the handshake that makes sure you are using encryption to connect. If I scroll up, you see we have a TLS 1.3 encrypted connection. As you can also see, we get the customized welcome message that we defined in the config map dovecot.conf. I'll show that configuration as usual above me here. Once that information is confirmed, we can log in into the mailbox with a login manual password.
the result we should get is a successful login. This login is a massive success. Congratulations! We have established a Dovecot system on our Kubernetes cluster, and you can and should be very proud of yourself, as that was no small feat. As I don't have anything else set up yet, such as an email that we could take a look at, I will wrap up this video right here. What is working? We have a fully functioning IMAP server that allows you to manage your own email data on your own server. The setup of Dovecot is a fully synchronized master-to-master setup with 3 replicas. The user setup is fully virtual that allows you to manage users in a database instead of worrying to create Linux users. What's next? The next step is to create a fetch mail client that will pull emails from our email provider and hand them over to Postfix and store these emails to our Dovecot instance. Then we have to set up a synchronization similar to Microsoft Exchange Server that will allow you to synchronize your contacts' calendars and emails to your phone and any email client capable of managing Exchange accounts. Until then, thank you so much for watching. I will see you in the next video.